Greetings. In this one we'll be talking about the algebraic structure of a monoid, which is an algebraic structure that's quite simple. So basically a monoid is defined as a set that has some operation to it, and it also has an identity element, and also so the minimal amount of elements is 1, of course, and it also has associativity, not necessarily commutativity. If it has commutativity, then it's called the commutative monoid. So we have some set S, and for some set S, and the operation, there is some operation of the monoid, so let's call that operation, I mean, it can be addition or multiplication, depends on the case. But let's for example say the operation is denoted by a circle, so it's an operation between two elements from the set back into the set. So an operation, binary operation of two elements, one element from the set S, which is the underlying set of the monoid, and another element from the same set into the set again. It can be the same element put in operation with itself, or different elements depending on the case, of course. But of course, if in the case that the monoid has only one element, it's of course just the identity in operation with itself resulting in the identity, which is a very concrete case. And a monoid, what can be thought of if you know what is a group? As a group that doesn't have inverses for the elements. So every group, for every element, needs to have an inverse, but the monoid doesn't have that. But of course, it must have an identity element, and it respects associativity, and not necessarily that commutativity. So the axioms for a monoid, basically, you want to define the properties that for any element in the monoid, or actually there exists some E in the monoid, so that for every element in the monoid we have, if the element E, by which I mean the identity element of the monoid, is put in operation with any other element or itself, first of all it commutes with it, and it does not change the element. So this is the definition of identity. And the second property is, for every A, B, C inside the monoid, we have A, B, C, or this, I mean, equaling, alright? So we don't need the parentheses for those. We don't have to write parentheses by convention if it's one letter. So this is associativity, and this is the existence of identity. And of course, the lowest amount of elements in the monoid is 1, because that would be the identity element itself. So that's that. Now we can have an example. And operation was this circle, so maybe if I want to follow that, with groups and with algebraic structures, we often denote the operation by only a space or nothing. We just write the letters next to each other. That means they're in operation with each other. But if I want to be clear, I can do this, right? I can put the operation mark there, like the circle, because I said the operation of this monoid is this circle. But I could just say, I don't have to specify this, and I didn't specify not the sign for the operation. And now let's look at some example. So that would be, for example, natural numbers with addition, and of course with the identity element of 0. So of course, I mean, for any ABC in the naturals, we have associativity, and under the addition, all right, like this, and also and this E in this case, I will call 0. This is the E, so I will call it a 0 for additive natural numbers under addition. As you see, this is the identity element under addition, and also for multiplication. So this actually would be also already an example of a commutative monoid, because multiplication and addition in this way standardly between natural numbers is commutative. So that's nice as an example. I mean, another example could be matrices on some ring with the entries from some ring under matrix multiplication. I mean, not necessarily commutative, but we do have associativity. We also have the identity element, and of course these matrices have to be compatible to be multiplied with each other. So that's that criterion. We know about that. So that would have some added details to it, but the idea hopefully is clear. And there's of course so many more examples. And one more thing that we should also realize: every group is a monoid, because groups are a subset of monoids. So every group is a monoid, because monoid is just a group with less restrictions. Namely, the inverses for elements are not required.